differential equations, growth and decay, differential equations. Here we look at the application of calculus in terms of differential equations. We use the method called separation of variables to solve very simple, basic differential equations. There are various differential equations that exist, and all of them require different techniques, different strategies to solve. Here are some of the most basic differential equations involves what we call separation of variables. We will apply that method to the growth and decay model. The neat thing here, and probably good for you, but in the course differential equations, we will spend time to prove the growth and decay model from the mathematics, and to show how the differential equations process is so important to all of mathematics. The growth and decay, exponential growth and decay model, typically what students see is y is equal to c times e to the kt to represent population growth. If k is negative, then we talk about we have decay. If k is positive, then we have growth. Again, in the course differential equations, we will prove how to even produce such a formula. I will not belabor that at this time. How to solve differential equations using separation of variables. If dy over dx is equal to mx divided by ny, then it is possible to separate the variables here, multiplying both sides by n of y to give us, and then multiplying both sides by dx to then give us n of y times dy is equal to m of x times dx. N is a function of y, m is a function of x. So basically we're trying to get the like terms together, get the x's, the x terms with dx, and then get the y terms with dy. Separate the variables in that fashion, and then integrate with respect to dx and dy respectively. Let's begin and solve these differential equations using the method of separation of variables. So here, multiply both sides by dx, so we end up with dy is equal to parentheses 5 minus 8x times dx. Now we integrate both sides. So this gives us y is equal to 5x minus, you integrate the 8x, you get 8x squared divided by 2, which ends up with 4x squared, and then plus some constant c. What about this one? Here, to separate the variables to get the like terms together, we multiply both sides by dx, and then divide both sides by x minus, about 6 minus y. So here we have 1 over 6 minus y times dy is equal to dx. Right? So here the variables are separated, so we integrate both sides. So the integral of 1 over 6 minus y dy is equal to the integral of dx. Well, to integrate the left side, you need to use a u du substitution. So let u equal to 6 minus y. Du is negative dy. So negative du is equal to dy. And so that gives us the integral here, negative 1 over u du, and that's equal to the integral of dx is just x plus some constant. So this is negative the natural log of the absolute value of u is equal to x plus c. This is negative the natural log of the absolute value here, u, is 6 minus y is equal to x. Let's let this constant be c sub 1, x plus c sub 1. The idea is to get y by itself, if possible. Sometimes it's not practical. So here we can write this negative. You can do it a couple of ways. You can divide both sides by a negative, or you can make the negative the reciprocal. So if we did that, we have the natural log of the absolute value of 1 over 6 minus y is equal to x plus c sub 1. Exponentiate both sides because of the inverse property. In doing that, e to the natural log, the inverse is there, so all we have left is the term, and just write that as 1 over 6 minus y. That's equal to e to the x times e to the c sub 1. And this is fine. We're going to just multiply. I should have just took that negative and ran it through. It doesn't matter, that the mathematics is still consistent. And so here, I want to make this just, this is a constant. E is a constant, raised to a constant is a constant. We'll fix that in just a moment. So I'm going to, well, let's go ahead and do it now. Let c equal to e to the c sub 1. This is 1 over 6 minus y is equal to c times e to the x. Now we just multiply both sides by 6 minus y, and then divide both sides here by that e to the x. So that gives us 1 over e to the x is equal to c times 6 minus y. So this is e to the negative x is equal to c times I want to make a jump. I don't want to scare you. Here, we're going to divide both sides by the c. C is a constant, so I'll just write it as c hat. Okay. So this is c hat times e to the negative x. That's equal to 6 minus y. Now, personally, I probably would have stopped this problem probably right here. But I want to be congenial to what you may see in the back of the book. So I'm going to add y to both sides, subtract both sides by this term here. So you end up with y is equal to 6 minus this constant times e to the negative x. And you call it c hat or whatever, it doesn't matter. It's still a constant, right? So let's call that a hat and make them a hat like this. And then I flipped it here. still a constant, right? Probably could have, again, fixed it and made it look not as complicated by just running that negative through right there. Either way, you get the correct answer. Let's go a little further. This is 1 plus x squared. This is times dy over dx minus 2xy is equal to 0. Multiply both sides by dx. We get 1 plus x squared times dy minus 2xy dx is equal to 0. Now, notice that this dy here is associated with 1 plus x squared. They're unlike terms. And this y is associated with the x and the dx. I'm going to divide both. I'm going to divide everywhere by y and divide everywhere by 1 plus x squared. And when you do that, you have 1 over y dy minus 2x over 1 plus x squared dx is equal to 0. Now we integrate here everywhere, integrate here with respect to the y minus the integral of 2x all over 1 plus x squared dx. This is equal to c. This gives us the natural log of the absolute value of y minus, let u equal to 1 plus x squared, du is the 2x dx. So this is minus the natural log of the absolute value of 1 plus x squared, and that's equal to c. And you can leave it as c, or you can write it the natural log of c. It's still a constant, so it doesn't matter. I'm going to leave it just the way it is. You can write the left side as the natural log of the absolute value of y all over 1 plus x squared, and that's equal to c. Or we better write that as c sub 1. Let's see a change. Exponentiate both sides, e to the natural log of the absolute value of y over 1 plus x squared is equal to e to the c sub 1. So the left side is y all over 1 plus x squared and that's equal to here c. Let c equal to e to the c sub 1. So you end up with y is equal to c times parentheses 1 plus x squared. Now on growth and decay, here on bacterial growth, the number of bacteria in a culture is increasing according to the law of exponential growth. What does that mean? That means that P of x, I guess P of t, where t is the time, p is the population, is equal to some constant times e to the k times t. So that's the formula that they invoke when they say the law of exponential growth. If it was the law of exponential decay, we'd just say negative kt, right? So part A, it says find the initial population. It says there are 125 bacteria, where P represents the bacteria, in the culture after 2 hours, and then 350 bacteria after 4 hours. So if you look at that for part A, we have 125 is equal to C times E to the 2K, and then it says you have 350 bacteria in 4 hours. So you want to find the initial population. The initial population is P of 0, which will give you C. Look at this formula here. If the initial population is when T is 0, so you get e to the 0, which is 1, so the initial population would be P of 0 equal to C. So we find capital C, then we got the initial population. We need to solve for K from these two expressions. So from the first one, notice that C is equal to 125 times e to the negative 2K, right? Now using that for the second equation, substitute this C for this expression here. So we get 350 is equal to 125 times e to the negative 2K times e to the 4K. Okay, good. So now this is 350 divided by 125 is equal to e to the 2K. As my cousin Valerie would say, okay. So now we here take the natural logs of both sides. Well, the natural log of e to the 2K is 2K, right? The natural log in e are inverses, so all you have left is the term 2K. And so this implies that K is equal to the natural log of 350 over 125, and that's divided by 2. Somebody's calling. We'll talk to them later. So now on your calculator, you can figure that out, that this is somewhere around 0.5148. 0.5148. Good. And so then, leave me alone. So C is equal to 125 times e to the negative 2 times this 0.5148. Now on your calculator, that comes out to be 44.64 here, bacteria. So P of 0 is equal to 44.64, the bacteria. And part B, this is write a formula. No problem, we got the work. P of T is equal to C, where C is the 44 point, well, better write, just write the generic information. So that is P of T is equal to 44.64 times e to the negative 0.5148 T. That's the model. Part C, use the model to determine the number of bacteria after 8 hours. So here, just let T equal to 8. So P of 8 is equal to 44.64 times e to the negative 0.5148 times 8. And that'll give you, I got 2,744.5 bacteria. Part D, this is after how many hours will the bacteria count be 25,000. So here we have find T. when P of t is equal to 25,000. So we have 25,000 is equal to 44.64 times e to the negative 0.5148, not times 8 times t. Can't look at the previous problem always. Times t, solving for t. So there we're going to divide both sides by that 44.64. Is equal to e to the negative 0.5148 times t. I'm going to solve for t. Take the natural log of both sides. So this gives us the natural log of this 25,000 over 44.64. That's equal to negative 0.5148t. Now divide both sides by this decimal. So you have t is equal to this negative natural log of 25,000 divided by 44.64. And then that's divided by 0.5148. And don't forget that negative. Now in your calculator, you got to be careful. This natural log here is only applied to these two numbers in the quotient. Then you take that answer divided by 0.5148. Don't forget to negate it. And what that does is interesting. K is not negative. This is growth. It was negated only to find C. That blasted devil just. Oh, it's needed there. I'm looking for C. But after we find C, P here has K positive. That wouldn't give you that number anyway. And I better check it on my calculator as well, just to make sure. Yes. So here we get 12.29 hours. Sorry about putting that negative there. I got carried away with that negative. But that negative for that exponent was only in solving for C. Here C is 125 times e to the negative 2k. Right? Otherwise, that k is positive. Again, growth, and that's what threw me off. It's growth, so k is supposed to be positive. If it was decay, then we'd have a negative k there. So we got the answers. Part A, here the initial bacteria is that. Then part B, this is the formula. Part C if T is equal to 8 hours, the number of bacteria is there. And then part D, if they give you the number of bacteria, can you find the hours? And you found it right there. Well, I think that should do it. I wish you well. Always go well, stay well. Thank you.